vectors.
So there's 400 of these images.
Yeah, I
Isn't that all?
Yeah.
Yeah.
I also see that.
We can also do this.
You also get the whole slide with them. And so there's each one of these kind of
Okay.
so we have 400 SDS files. All of them are labeled like this, where there's
I think the vectors.
you have the labels of
They just
Oh yeah, it's better. I like short. Oh,
Yeah, excellent.
the annotation of the whole thing was performed 2 minutes ago. I have a very disagreement with this. Each image has a corresponding list of labels that correspond. So yeah,
So they have
Not negative, XOR. Not XOR. Yeah,
yes, powers.
Yeah.
How's machine learning going?
yeah, because look at the, I can state tissue
Yeah,
with certain stains, but rice tissue with this stain, I can't tell the difference. So yeah, we follow this. We have all this data. So I guess one thing that we do and that question we have to figure out is this going to be well, there's classification problem. There's one before
I don't know, but not really
segmentation problem.
Yeah, I'm not sure. I think so.
Right.
But then, because the programming has been started,
Yes.
even the data for systems.
Hi. Surjit, how are you? Good, how about you?
Like this, it was with we're screwed.
You're always running. It's like a challenge. Yes, I can do like you to like 9%. That's been a lot of comfortable. So we have
Okay, let's get started. How's everybody doing? All right? Good. How the last couple of lectures go? Okay.
Alessandro said that the GANs one went really well. He feels like he's an expert in GANs, but that variational autoencoders was a little rough. Is that feel okay? So he admitted that, and I'm going to spend part of the day going back through that material. Hopefully that can help clarify some things there. And then I'm going to expand on that on a different idea for generative models that combines both ideas from autoencoders and ideas from GANs. But before we get into that, how are we doing on homework? We doing okay? Some of you have already turned it in, well done. And are begging for more. So there'll be two assignments for homework for like 2 notebooks. One of them's ready, one of them's not quite ready. But I can put the one that's ready up if you're desperate to start homework. The trouble with that is that it's for the topic that we're going to be doing next week. So
What topic is that?
recurrent neural networks. So we spent a lot of time doing lots of convolutional networks, and now we're going to go into recurrent neural networks in a couple weeks. Okay. Good. How about projects? You okay on projects? Get your project proposals put together? Okay. Good. All right. Well, if there's no other questions, we'll just get going here. So literally, I'm going to be showing like the same slides I believe were shown a week ago today for variational autoencoders, but hopefully that's good. Just we can talk more about that.
Would it just lights and buffers?
Yes. Thank you.
This one.
Okay. All right. So, okay. So the last part of our 4-part generative models series, we're going to eventually get to adversarial autoencoders. So notice how 2 names are combined into one here. But we won't do that before we go back through variational autoencoders. Okay, so remember what we started this whole thing with in part 1 was this pretty simple idea of learning how to generate data from, or generate pixels, basically the intensity of a pixel, the color of a pixel, from the previous pixels. That's what the pixel CNNs were, and again, the idea was that this is what's known as a fully visible belief network. But the point is that it's just saying like, hey, for every pixel, we look at the pixels before it in some way of ordering, and we make a prediction given what those values are, and then the product of all those distributions is the full likelihood of our data under the model. And so again, like what this is saying is that what we're trying to do is maximize this likelihood, right? So so the data is X, and we're trying to maximize the likelihood that data was generated by our model. And that's like a theme in when we're doing generative models. We often think of it from a probabilistic standpoint, and we often try to do this thing. We try to optimize this likelihood of the data. This is also known as the evidence. This just if you do like Bayesian statistics, this value right here, the likelihood of the data is known as the evidence. And so, these simple models have this really explicit way of computing that. Each one of those P's can be a neural network. It could be any parameterized model you want, and theta being the parameters of that model. And there are lots of methods for optimizing. If you take this like a kind of a more advanced statistics course, or some other maybe statistical mechanics course or something like that, you might have run into something like this. Okay, so VAs, variational autoencoders, they do something similar to what we saw with the fully visible belief networks. We have an expression for the evidence, but what we're doing now is we're we're thinking of our data as being generated by some unknown, unseen, latent factors Z. Okay? So Z, so this is, when you start reading lots of papers in this area, or statistics or whatever, you see that like variables are commonly used to denote similar ideas. So X is always data, Y is always labels, and Z is always latent variables. So if you see a Z floating around, you know you're talking about latent variables. And the word latent here means hidden. It's something that's explaining our data, but we don't observe it directly. What we observe directly is the data, X, but we don't observe these latent factors. But these latent variables, these latent factors Z, in some sense, like generate like they are the explanation for the data, and therefore you can generate the image or the text or whatever it is that we're trying to model here from these factors. And so what we have is we have a likelihood of the data given latent factors. By the way, you probably already noticed this, and maybe you already brought this up, but like I totally use the words data interchangeably, and I don't know why. I don't know why I use one or the other, but like when I say something, like one of them sounds right, I just say it. So if that's weirding you out, it also weirds me out as I listen to myself, but I can't fix it. So okay. So anyways, we have this likelihood here. Again, think of this as something as like with these latent factors. Think of these as like this is some vector of numbers. What's the likelihood that this data was generated by these values? And then what we have is some prior probability on the latent factors themselves. So some of these latent factors will be likely. They'll have high probability. Some will have low. So it's just some prior there. And if you've done Bayesian theorem, Bayesian statistics, you start seeing things like this, you recognize some of the forms here. And we're gonna rely on Bayes' theorem a couple times. So, anyways, so this is another idea. So, if we had these two models, then we could do this integral over Z over the latent factors, and we could get our evidence here, and then we could maximize that, and in that way train a model.
What's the latency?
What's the latency? There's no latency here. There's just latent.
Yeah. What is latent inside? Like what does it represent?
What does latent mean? Yeah. So again, like these are just hidden factors. So let's say think of anything like think of the weather. You observe the weather. You observe it by measuring temperature or humidity or something else like that, right? But there are factors like how the density of the air, there's much more complicated factors behind the phenomenon that you observe that's generating the measurements. And so these Z, we don't observe these directly, but they are there, and they are the thing that's trying to. Or if we knew those, we could know. It's like we would have the explanation for why we observe the things that we observe. And in Bayesian inference, what you're often trying to do is that you are trying to, from your data, infer these latent variables. Because if you could get access to them, then you would, in some sense, have the full explanation for everything you're seeing, and now you could totally model everything. And this is something that we're going to see more and more as we go through this lecture. And this whole area of generative models is sort of based on this idea. Anyways, so if we could do this integral, we'd have this, we could maximize this, and we'd be in good shape. We could run all kinds of generative models. Notice that this is a generative model in the sense that this function right here, you can think of it as you're generating the data from your latent variables, right? So latent variables are some low-dimensional representation of your data, and this P of x given z is like the function that produces the most likely x, say, or like a likely x. Think of it probabilistically, like you're sampling from this distribution for the given z that you have. Okay. So this is the generative part. Just in the same way as up there, instead of the z's being latent, we actually observed all of the previous pixels, the previous pixels, and then we generated the next pixel. Here, it's a very similar concept, except we're just assuming that these things exist, and we are generating from them.
Yeah, so here, theta generates z, but as well as it also
Theta is the parameters of this probability distribution. So think of those as like this probability distribution is a neural network, and those are just the weights and biases.
So theta is related to z as well as x. So.
Yeah, that's true. I mean, this is just saying that this is some function whose parameters are theta. That's all. And maybe what you're saying is something, or maybe what you're getting at is something like the fact that we also want to learn the parameters of, like, not just the z, but we want to learn the parameters of the network. So that's true as well. That's what the training is for. Okay. Yeah. So unfortunately, this is a bit tricky to do. Anytime you see like real integrals, you should already be feeling sad because this is going to be hard. Derivatives are easy, integrals are hard. Especially when your functions that you want to integrate are can be very complicated. So let's take a look a little bit more at that. So, okay, so this is something that hopefully you covered pretty well with Alessandro, and I already kind of covered it before as well, just the idea of autoencoding. Now thinking about this in terms of latent variables, you know, I'm just going to skip a couple of slides ahead here. Yeah, so the idea of autoencoding is we have all this data, so this is just a sample from our data distribution. And what we want to do is we want to like find these latent variables, these hidden features that sort of explain the depth. And the way that we get our networks to do that is by taking our input, having some sort of network architecture that takes this like high-dimensional data and compresses that down into some low-dimensional representation z. So think of this as being, you know, our ImageNet images, so something like 228 by 228 by 3. And what we want to do is we want to compress this down to something, you know, quite small, like 64, like a vector of 64, right? So whatever 28 times 28 times 3 is, or 100, or 228 times 228 times 3, I don't know what that is, but it's large, very large compared to like 64. So what we're trying to do is we're trying to compress that, but like there's a lot of ways you could do that. You could make this could be like the dumb encoder that takes all these and makes this a 0 or something like that. That's not very informative. You want this to be very informative, and you want it to be able to explain all the variation in your data. And the way that you do that with autoencoding is you say, okay, great, I have this network that I compressed to this small representation, but now what I want to do is decompress it or decode it back to the original image. So I have this function that encodes, I have this function that decodes, and then I supervise the whole thing just by saying I want the output of this whole process to be equal to the input. So it's still a supervised learning task because you're supervising it with the data itself, but it's considered unsupervised because there's not like an additional label here. It's just, you have just the data distribution, and you're supervising it with the data distribution. So that can be a little bit confusing, but hopefully you can see the difference. Like if we don't have, in doing this, it's not like we have, in this particular case, we don't have like the additional label saying like what class this is from, like if this is a dog or a cat or a car or whatever. This is just my whole data, compress it all to something small, and then decompress it to the original sizing and supervise this so that it looks like the original image. And we learn how to, we've seen lots of these already where you can imagine how to do this maybe with like tabular data. So you just have vectors here, and you just have a bunch of fully connected layers, each getting smaller, and you get to here, and then each getting bigger. But then you can also do this with convolutional networks by using, in the decoding, by using the transpose convolutions, to increase the spatial extent of each of the feature maps. So here's an example of a something or other like this that was trained. Here was the input data. This is from CFAR, probably CFAR 10, and those are the reconstructions. So they look a lot like the original images, but they're just fuzzier. They're not as sharp as they could be. There's a reason for that. We won't get into that just yet. Okay, so that's the idea. And again, the whole idea here is if we can do this pretty well, then we can say that these features here, that's what's sometimes called the bottleneck layers, like the smallest layer. You're sort of trying to fit all this data through a bottleneck. You can think of this as being factors that explain the data that you're looking at. So these are the hidden, the latent features that explain this data. Unfortunately, when doing this, you don't also have an explanation for what each of, like, think of this as some vector of size 64 or 120 or something like that. You don't also have like a data dictionary that says this feature is, corresponds to the color of the object or something like that. There's nothing simple like that. It's this process of training it so that these reconstructed images look like the original images, shapes that in such a way just to make it the most informative. But you also you don't have this way of interpreting it. So that's unfortunate, but that's the price you pay for like ultimate power using neural networks.
Just a quick question, like because the feature set has the different size. So does that mean it's just always mean the feature is just a subset of the input data? Like why is not why not the features have the same size?
Why don't the features have the same size as this?
Yeah.
If they had the same size, there would be nothing to learn, right? Like if this was the same size, then all these transformations would just be identity transformations, and you'd perfectly reconstruct the data. You haven't learned anything. So like a part of like there are some deep connections between like compression and information theory. And if you ever take any courses in that or study anything there, you'll know something about like Shannon entropy and how. Yeah, I mean, this depends on a lot of things, but anyways, let me just believe me that there is this relationship between compression and information. So what you're hoping for in your data is that you don't need all the information from every single pixel to be able to reconstruct it. If you do, then you have this very, very entropic like language or like alphabet or whatever that you're working with that you're trying to encode. But like you don't need that, right? Because like look at these images, right? Like huge regions of these all are like monochromatic, right? They're essentially the same color. You could just think in your head, I mean, like this wouldn't work very well generally, but you could see how like you could, in any one of these images, you could really compress what's in that image just by saying like, here are instead of specifying the color for every single pixel, you could say like, everything in this region is approximately of this color, right? So you just specify the region boundary and the color, and that would be a massive compression of the information in that image. That's kind of a simple way of thinking about it, but there's also like, lots of other ways you might think about this, like, you could start to learn that you have some sort of feature that's indicating that hey, you have a kind of animal in this area, and this kind of animal is of a particular class, maybe like a horse, and so a horse is going to have to look in this this way, and so you've compressed again all the information around the pixels of that horse into something that's more like a description of the horse, and that's what these factors. That's what you're hoping you're getting out of like these factors, these features here, these compressed features. And it turns out that I mean, that isn't perfect reconstruction, but there's basically a horse shape of the right color with the right background there. I mean, it's captured a lot of it, not all the detail. And when you did the GANs and you see the examples there, like the GANs are another way of doing something very similar to this, although it's different. And I'll talk about that when we get there. But they're much sharper. You get much sharper images out of those usually, And that's because of its ability to be able to learn much more complicated distributions for this space here. Anyway, we'll learn more about that. Or we'll talk a little bit more about that later. We get the point here? We get kind of the basics here. All right. Cool. Oh yeah. Hey, look, we used that function as our loss function, and we optimized that. Okay. So we'll skip through that. All right. So what the heck is this variational part? Well, so the autoencoders you can so you can just train an autoencoder. There's no need to really think about anything probabilistically. You can just think about there being like you're going to learn some encoder, then some decoder, and you're going to put them all together. You're going to learn it all end to end through by optimizing the reconstruction error. So the L2 difference between the input and the output. Variational autoencoders sort of take this idea and interpret it probabilistically. It's essentially a way of regularizing the whole procedure, but also gives you a much better generative. There's a much better generative story here. Like the generator that comes out of this ends up being a lot more robust and useful as a way of kind of sampling from the distributions here. So here's how a probabilistic spin is put on autoencoders. The way to think of this on the decoding side is we have exactly the same picture. We have some space of latent features that and a set of transformations that turn that into something that comes from our data space. And we have similar notations as we had before. But the point here is we say, okay, you know what? Let's really imagine there actually is a distribution for our space. So we can't. So we don't just assume that every single feature vector in this space is equally likely to appear. Let's assume that it's got some sort of distribution to it. So we're more likely to sample from certain parts of the space than others. And then once we sample one of those, then we can also think of sampling the data from so given our sampled latent features, we can now take that and sample from the conditional distribution that is sampling our data, so like the pixel values given that particular feature. So we've actually only made things more complicated. Why would we do this? Let's go through it. So yeah, intuition, we just talked about autoencoders, so you don't have to remember that much. But again, it's this idea of generation. In generation, it's often really useful to think of it as like sampling from a distribution. And here's why. So in this, what we're trying to do is we parameterized these distributions in some way, and we're trying to learn those parameters for that parameterization, for this generative model. How do we represent these models? So it's often the case that what we do is we, for the prior distribution here, we often make this as simple as possible. We could choose anything here. We could choose anything we want here. We can't choose anything here, right? So like, if these are images, there's only certain arrangements of pixels that will look like horses and cars and things like that. But here, because we learned this thing all end to end, we're able to kind of shape this kind of however we want. So it's often the case we say, you know what? Let's have this be something really simple, like standard Gaussian. So mean zero. This is multidimensional, so you're going to have a covariance matrix, but we just assume that that's like a diagonal. So there's no covariance between the different features. That's what we hope to see. So all the features here are independent, and maybe they all have like the same variance, so we call it variance 1 or something like that. So we often do that just to make this as simple as possible. And it's not terrible to imagine that because for a couple of reasons. One is we do this all the time already. So any of you who've done any sort of data or dimension reduction with like tabular data, you've almost certainly used PCA, so principal component analysis. And what's principal component analysis? What's its job? Its job is to basically give you a new coordinate system for the vector space of your data, in which two things are happening. One is you have some sort of decomposition of the variance from like this, this variable has the highest variance down to like smaller variance. And again, like for that data, the factors are all orthogonal to each other. So you have independent. So you've done this change of basis for your data. So now you have this new coordinate system for your data, in which all of the features now are independent of each other, and they have no variance. And often, if you don't care about preserving that, you'll do the dimension reduction by kind of removing the features that explain very little of the variance, and then you might even like whiten that, so that now you rescale the features so that everything has the same variance. There's lots of ways to do this, but this is often a very useful situation to be in, where the lower dimensional representation of your data is each of the features is independent of all the rest. Just makes it's just a simplicity thing. So imposing a Gaussian here is a standard normal Gaussian, standard Gaussian is really useful. And you might, again, like this is really not. Yeah. When we talk about these things, it's so interesting, right? So what we hope is, we say that we have faces, right? So what we want these things to do is explain things about the face. So like, this shows things like pose or how much smile, and sometimes actually we get that out of the features. We'll see some examples around this, but often we don't, and it's often the case that these are not so readily like interpreted, but sometimes they are if the data set is simple enough. You might imagine that pose is really independent of smile, for instance, right? So like I can be posed any way I want and be smiling or frowning or whatever. Like those two aren't necessarily correlated, although you can imagine how they could be correlated, or how how wide your eyes are is correlated with like how wide you're smiling or something like that. So, anyways, we often choose really simple priors so that we're forcing the features in our latent space to be independent of each other and on the same scale. So, okay, so what do we do then for the conditional network? We think of as our decoder, which is the thing that we sample from given a particular set of latent variables. And that's the thing that's complicated, right? That's the thing that has to do this really like highly nonlinear map from the set of features like that could maybe be pose or how much smile to the people picture, the actual image that we're trying to regenerate. So here we're going to need something powerful like a neural network. How do we train this? Well, remember we have this evidence term. It contains both this prior and this conditional. So, like, we kind of start from there. We're sort of hopeful. Maybe we haven't done a whole lot of Bayesian statistics, and we don't know that integrals are hard. So, what's the problem with this? The problem is like these integrals really are intractable. So, hey, simple Gaussian, especially if it's like standard isotropic, like that's going to be super nice. Even for like a really complex network, the dependence of x on z is not that complicated. At least it's pretty straightforward to do a forward pass in the network through these things. The trouble is, as soon as you want to do this integral, this space is really, could have many dimensions, and it could be not compact, whatever it is, and trying to do this integral over these, basically computing that likelihood for all the z's is, given x, is totally intractable. And we might think, okay, well, the thing that we might really care about is we just want to be able to explain we want to just be able to do this encoding really well. So we can write that down using Bayes' theorem like that. But the trouble is that you also, again, have that the evidence there of that data likelihood. And so while the first two terms, again, are tractable, that thing's not tractable. So just appealing directly to the thing itself is not going to work. So how do you deal with this? So there are a couple ways of dealing with this. If you don't have any advanced statistics, again, or statistical mechanics, you might have learned to use MCMC methods. So ways of sampling, ways of updating your parameters that depend solely on sampling from these distributions. So this is Markov chain and Monte Carlo methods. The class is not about that, but there's well-known old, maybe decades-old ways of doing this, where you can basically you can sample from the correct distribution for you can learn these weights. Basically you can learn these in a serial way. You continually update these weights until at some point you basically converge to the right distribution, and then you can sample from that and get all the statistics that you want. That is a totally legitimate way to do it. The trouble with it is that all MCMC methods are serial, meaning that they have to be done, you can't be parallelized. You can't parallelize them, but they're approximations, and they end up being really difficult to work with. And so they take forever to learn, especially if you have a lot of data. So if you don't have a lot of data and you have a pretty good idea of how you ought to parameterize your distributions, and you're okay going with MCMC methods, but if you don't want to do that, then instead what you do is you take a variational inference method or approach, which is that you actually try to learn this distribution directly. And what you do is you basically say, you know what, I'm gonna choose a family of functions. These again will be neural networks. Choose a family of functions that I'm going to try to make approximate my the posterior that I want. And if you can do that, then this is your encoder. And we already said that we can, this is fairly easy to work with. It's going to be another neural network. Then I have my decoder as well, and I'd be good. So this idea of directly trying to approximate the posterior distribution, this is now this is basically like doing inference, saying, given all this data, what are the latent factors associated with it? If I try to do this directly, then I actually have a chance of doing this. Although it's definitely going to be an approximation. Okay, so how do we do this? So we have two networks. In the full probabilistic way of doing this, both these networks are going to represent distributions, and our encoder network, which is going to take us from X to Z, so from our data to our encoding, or latent factor Z, that's going to be a neural network. And if we assume that it's going to be, if the data is Gaussian, then, or sorry, the encoding is Gaussian, then what we actually want to do is just learn a mean and covariance matrix for that, and then we have the distribution, because these are the parameters of that distribution. These are like the phi in this case. You could also imagine, and these slides have this. You can also imagine that we could do the same thing for the decoders. We go back from latent space to the data space, but so that the data is generated conditionally as a Gaussian, But the truth is that like while you can do this, and like while this was part of like the original formulation of VAEs, most like modern VAEs don't do this. They just treat this case deterministically. You just have a function going directly from Z to X, and the only probabilistic part is in generating Z and sampling from it. But you know you can imagine it being that way. So like if your parameter as a Gaussian, you just remove the Gaussian parameters. So yeah, sometimes these get different names: recognition and inference for the encoder network, and generation of the decoder network for obvious reasons. Okay, so here's the important part of all this. Is this next piece? Okay, so what we need to do is we need to get an approximation that's going to be good enough to give us decent results here. And so here's the derivation here that it's one of those, this is totally like a math thing to do. It's like, I'm going to do this derivation that's going to look like all mysterious. Somebody at some point worked it out, and it did not work it out the way that you're going to see it. They worked it out in a totally different way, but this is like kind of a way of now explaining it. So if it doesn't feel intuitive, it shouldn't. It wasn't discovered this way, but then you can once it's discovered, then you can redo things like this. So, okay. So what we want to do is we want to maximize the evidence or the data likelihood, and we're going to do the log likelihood here. That's just a order preserving transformation. So we optimize one, we optimize the other. Okay, so I want to optimize that. So first step here, I do something totally non-intuitive. Is I take this expectation of that evidence over some sampling of Z. So this is sampling from this this recognition network Q that I'm going to learn. The reason I can do this, I can just put this out here, is that the evidence doesn't depend at all on Z. So that operation is basically a no-op. The log evidence factors out. The expectations becomes a 1, and so it's just a nice number here. So why do I do that? Because I'm going to start playing around with all kinds of identities and produce something else that would be useful to look at. So I truncated this here. This is still sampling. These are still sampled from this encoder network I'm trying to learn. But what I do now is I re-express my evidence using Bayes' theorem or Bayes' rule. So if you look at the P of theta there of x, if I look at this, if I were to multiply this denominator by P of x, then what I have is P of x times z given or P of z given x, and that's equal to, by Bayes' rule, just switching those things around, the probability of z times the probability of x given z. So, and those are both the joint distributions between them. Anyway, so this is just using Bayes' rule to kind of produce some other things in here that again shouldn't feel so intuitive yet. But there you go. We then do something totally non-intuitive. Let's just put some more stuff in there. This is a 1, right? If we multiply by a 1, but this 1 is a special form, we now get the Q that we're sampling from in here. And now once we've done that, I can just do all kinds of fun, exciting things. So I can now start rearranging all the terms in here. So I have this log here. So so it's log of everything that's in here. So so we're going to separate this out into 3 terms. The first term is just this log of this guy here, the likelihood of x given z. That's what ends up here. This is a linear operation, so this will separate over these pieces. Next part of the next term that we're going to get is we take this numerator and this denominator here, and that is truncated in that way because the let's see, why is that? Why do we not have that given x? let me come back to that in a second. So, oh, no, sorry, I did that wrong. So what, I'm taking these two right here. Sorry, these two right here, and then I have a negative sign up here, which flips the numerator denominator. Sorry. So I take these two guys right here. It should be like this. That would be the plus, and then I switch the numerator denominator. And so that's why I get a negative sign out here. And then I have whatever's left over, which is that term and that term right there. Okay, so now I've got all these three terms, and nothing looks clear. Actually, everything looks worse than when we started. But it turns out that these are all actually recognizable things that we can work with. So before I go on, does anybody want to be brave and sort of like talk about anything here that we see? Just like say anything about what they recognize here. There's just like all kinds of letters. All kinds of letters. What's this right here? We're sampling, so we're taking an expectation.
That's a decoder.
So this, yeah, so this is our decoder. Exactly, good. This is our decoder. And we are taking an expectation of this likelihood over z's that we are generating for that particular data point, right? So given a data point x, we have some network that's going to allow us to sample latent factor z from that, and then we're going to calculate an expectation as we sample from them. We're going to calculate an expectation of those, the expectation of this log likelihood of the data given those z's. So this term right here is some measurement of how well we're doing reconstruction, right? My q's encode to z for that data point, and then my p here decodes back to x. And so for the likely z's that I get when sampling from q, I also get very likely x's for that, or sorry, I should say differently. I get a high probability of having reconstructed that data point from those z's, that I'm doing reconstruction pretty well. So it's a probabilistic way of thinking about like the reconstruction error. What is this right here? You want to be brave? Just try. Importantly, it's truncated here, but remember, I'm sampling my z's from q phi, which also appears right here. So this is like an integral, over with respect to the distribution determined here by this density. So I have something like information theoretic there, as well as here, actually, because I've got that there. Have I gotten rid of any of the complexity of the computation at all in this? Can we do this right here? Can we compute this piece right here? This is going to be a neural network, so we can. So Q phi is a neural network. So we'll be able to sample from that, and we'll be able to reconstruct this neural network. So like this is computable. We can approximate this expectation by generating a bunch of z's from that using that network, and then computing this likelihood, this log likelihood from it. So we can do that. Same thing here. This is that same network, so we'll be able to generate from it and also compute its values. And we'll be doing that simultaneously, so that's no problem. And then this is just some prior that we showed, like this is just our Gaussian. So we can compute this thing as well, no problem. Again, we'll just approximate this by sampling a bunch of z's and taking the appropriate average of all those. How about this? Any problems here? We do have a problem because this is our posterior that we said depended on the evidence itself. right? So this is intractable. So that makes sense. This whole thing was intractable from the beginning, and we just pushed the intractability into this one term right here. But it turns out that those last two terms are recognizable terms from information theory. They are KL divergence terms. So at the beginning of the course, we kind of briefly spoke about KL divergence, and hopefully you've seen this before in the probability class or statistics class. But it's some kind of metric. Well, I shouldn't use the word metric. It's not a proper distance, but it's some way of measuring the difference between two distributions. And the important, one of the important properties of the KL divergence is that it's non-negative, so it's either 0 or it's positive, and it's only 0 if the two distributions are equal to each other. Almost everywhere for mathematicians in the room. But so it's almost like a distance function in that sense that it's if they're not equal to each other, if these two distributions are unequal to each other, you get some non-zero value here. The reason why I thought a distance or a metric is that it's not symmetric, and you can kind of see that in the log. That like if you were to switch these two things, then what you would get is you'd be sampling from one of the other distributions, and then these would swap. So you get a change in the sign, and you'd be doing a different integral entirely. So they're not symmetric, but at least you have this nice property. And why is that good? Well, this term right here that's causing us all kinds of problems. This one right here, because it's got this posterior in it, we at least know that this term is either 0 or positive. So we actually have now a bound. We can use that property and recognize, these are all the things that I was just saying. We can just assume that this thing right here, is 0 or it's positive, and then just take this part that we can work with that is tractable, and just recognize that this is going to be a lower bound for our evidence, for the log evidence. And so now that we have that, we can just optimize this. So if we just optimize this, if we just make this as large as possible, we at least know that we're pushing out a lower bound of the evidence. So we're not directly optimizing the evidence, but we're optimizing a lower bound for it so that we know it can't be any lower than that bound. And that's the best we can do. And this is actually the variational part. The fact that we're using this approximation for our posterior and doing this approximation makes this a variational method. Okay. So ask questions or say like I totally don't get it or whatever, so we can try to work to clarify this. This is really important. We want to optimize that. We can't because of that intractable term, but by doing all this fancy math, we're left with this piece that is tractable that we can work with and optimize.
I think the term is intractable. Like we can convert the probability of z given xi into probability of xi given z into probability of z by probability of xi.
Are you trying to make an argument that this is going to be tractable?
Yeah.
No, it's not.
Because
this is not tractable.
Because the denominator, that term, we can convert into another form by using base theorem, right?
Yeah, but the point is that you're always going to have some piece in that's going to be intractable, right? You're going to be left with either the evidence at some point, or you can't get away. You can't use base theorem to get rid of intractability. There's not a real conservation law. There's a conservation law here of intractability, and we've just pushed it into one of the terms here. But yeah, there's no way to get around that.
Which parameter do we want to learn? Theta or phi?
We're going to learn both. There's going to be basically two networks, right? We typically think of this as all as one network. Think of the autoencoder, it's all one network. But if you break that network up into kind of two pieces of the encoder and the decoder, we've got the pieces of both. So we want to learn both. We're going to learn them together. Yeah. Does it make sense that this is tractable? Did we get far enough into that to understand that all the pieces here are pieces that we're gonna parameterize either through complicated neural networks or through like very simple parameterizations like Gaussian distributions. Okay. And does it make sense too that like what we're doing here is we're optimizing a lower bound? So it could be the case that even though like we optimize this as well as we can, we still might not have a very optimal log evidence. It's just the lower bound, right? So we're just pushing from below with some possible space in between. But when things are intractable, so these are we can thank the physicists, the statistical mechanical people. What is it? Mechanics? That doesn't sound right. The people from statistical mechanics who kind of came up with these ideas, first in trying to solve complicated like states of gas and equations and things like that. But now we're using them here to train neural networks. Okay, so this piece right here, this is known as the elbow. It's the evidence lower bound. So evidence lower bound, it's the elbow. And you'll see the word elbow now in various papers from this work. And again, it's only this piece right here. We're just going to ignore this, and we're ignoring it, knowing that it's non-negative. So we have a good lower bound for our low evidence. Okay, great. So what do we do with that? Yeah, we talked about this. This piece, this part of the loss function is going to force good reconstructions. This part of it, let me say this more carefully because I didn't say this next part. So we already talked about this, how this part is going to force better, like as we maximize this, what you have to do is, given your encoder, this decoder is learning to produce the original data point. So the higher that the likelihood is that we produce the data point, the better we are reconstructing. So this is forcing good reconstruction. This right here, notice that this is also a divergence, a KL divergence term, but it's negative. So as we maximize that, that means that we're minimizing this. So that means that we're pushing these two distributions closer to each other. So what that means is that for every data point, what we're doing is we're encoding this we are sampling z's that are closer and closer. So this distribution of this is getting closer and closer to whatever we chose this to be. If we chose this to be a very simple multivariate Gaussian, then that's what it's going to be forced to be. So this is how we enforce some sort of regularization on the latent factor space or the encoding space. So those are the two pieces of variational loss function, and the two forces that are at work here. And notice that one's gonna cost us. By forcing these things together, there's no guarantee that that's actually going to make this be a better decoder, right? They're not necessarily linked together. But what we're trying to do is we're trying to create for ourselves a really nice latent space so that the factors are independent, or as independent as we can possibly make them, and they do a better job of explaining their data, each factor. Okay, so putting it all together. So we're going to generate the parameters for our Gaussian and sample from that. So that's for Q. We'll sample from that. Now we have a Z. We're now going to reconstruct, and again, this is using a probabilistic way of reconstructing, although this is definitely not used much anymore. This is usually just done deterministically, this is just a straight neural network, going straight from the input to output. But you can imagine this way, and you can sample the data from there. That gives you that idea there. Okay, so what Oh yeah, so for every mini batch, how's this actually trained? For every mini batch, you actually compute, you just do the forward pass and the backward pass as you would normally do. There is one kind of sticky thing here, and that is, let's see, do I have it here? I think I have it later, but I'm gonna say it now. So, because P and Q are parameterized by neural networks, we know how to backprop through them. But we do have the sampling stage, and backpropping through sampling is not a thing that we know how to do. Right? So, how do you get around that? So it turns out if you use these really nice Gaussians, right, you can easily get to the Gaussian with this mean and this covariance matrix by a simple linear transformation of the standard normal with zero mean and diagonal, like identity covariance matrix. And so you can sample from this constant distribution, and then do a change of variables to get you to this normal distribution with this mean and this covariance matrix. And therefore, the sampling happens outside of the sampling happens outside of the computation graph, which is sort of nice. This wouldn't work otherwise, because you couldn't backprop through the operation of sampling. Okay, so let's, so what comes out of these things? So this is like a representation. So let's imagine that we made our latent space be two-dimensional. Okay, so it's like a two-dimensional Gaussian. Yeah.
Are we assuming that our distribution, which is present, that is normal distribution? It can be anything, right?
You can make it anything, but the reason why we always do normals is because there's a really simple story for doing this reparameterization trick to be able to do this, to put the sampling outside of the computation graph. There is a way to do this for more complicated distributions. We're not going to talk about it, but there is a way, but it's trickier. So anyways, let's imagine that this was, we just imposed a simple two-dimensional Gaussian on this space. Okay, so what do we have? So what this is right here, think of this as like our two-dimensional space. So these are, in fact, I think I have to see the build. We have one direction being like the first parameter of z, the first entry of z, and then the other being the second. Yeah, or whichever way I have here. The point is that for every pair of this z1 and z2, our network will generate an image correspondingly. So we train this on MNIST. What we have, in a very simple way of training this, is so if I fix like z1 to be here, and I start to vary z2, what I have is for values of z2 to less, let's say, think of this as maybe like the origin being like right here. So for negative values of z2, I'm getting 7s. But as I change the value of z2, and as I increase it in this direction, these 7s kind of continuously change into 1s, and these 1s stay 1s, but they continuously kind of change into more and more slanted 1s. So all of these, none of this is necessarily data that we actually saw in the data set, right? Like no one of these is actually an exact image of what we saw in the data set. But what we learned to do is we learned to generate stuff from our data set, but in a parameterized way, in a way that's explained by two variables, z1 and z2. So for this z1 and z2, I get a 7. And and for this value over here, I get a kind of ugly-looking 6. It's kind of like an 8. And up there, I get 0s, and then I get some 2s. So for the different values of these z's, I'm generating a different image. So in some way, these two values explain our data distribution. And the explanation is hard to give in this case, but you can just kind of see how, like in this direction, you're getting both a change in the number, but also like a tilt to the right. And in this direction, you're getting, I don't know what you're getting. You're getting something that's transforming you from, like it's adding a loop here to these 7s. That sort of changes as well. And I don't know, just in these different parts of the space, you're getting a different you're explaining, you're getting a different number, a different sample from this data set. So we are generating MNIST digits here. We're generating data from that data distribution, parameterized in 2 dimensions. So again, think of it as like we are explaining the MNIST data set with just 2 variables, which is pretty cool, actually. You can do the same thing with other data sets. This is the Toronto Faceless database. So you train on this, and this probably had higher dimensions, but we're just picking out, like we're fixing all the rest of the dimensions and just picking out these 2. And you can see how, at least in this part of the space, as I'm varying like Z2 in this direction, I get, if you look this whole direction, I basically have faces that are looking to the left over here, and then as we go, that face starts to look more to the right. And as I go this direction, I'm frowning up there and I'm smiling down here. So again, like this idea of like head pose and like degree of smile was an important factor of variation that existed in this data set. And we learned to parameterize that through doing this variational autocoding training procedure. So that's pretty cool. Like again, we're explaining this data set in very few parameters. Okay, questions about that? Yeah.
My question is about sampling from the distribution on one side. So basically, your mean and your standard deviation defines the distribution. What you were saying before is you can transform it to a Gaussian distribution so that you can then take samples.
Yeah, let me just clarify that real quick. So the way this is done is that we actually learn the parameters of a Gaussian, right? So like we learn a mean and we learn a covariance matrix for a multivariate Gaussian. And then what we do is we don't sample from this distribution. What we do is we sample from the standard normal distribution, and then we turn that into a sample from the distribution, the Gaussian described by this mean and this covariance, by multiplying by the inverse of the covariance and adding the mean. There's like a simple that's I guess that's true for diagonal matrices. For non-diagonal, I guess you'd have to do like the square, like the square root of that on both sides. These would need to be positive definite or positive indefinite, which they typically are, if you've done this right. And so you do this transformation, and now the sample that came from here is now a sample from that distribution. And so.
And then the sample is used in the training, right? To.
Yep, exactly.
To create the.
So
what
now
converts it to the images.
So now, so in this case, I'm sampling again from this. So there was a sampling that happened here to get the z from the parameters for this distribution, and then there's another distribution up here that another normal distribution that I'm sampling the pixel data from. So there's two bits of sampling happening there. Okay. So you can train this on all kinds of data sets, and you can learn to generate data. This is not nearly as good as like GANs. Hopefully you saw a bunch of examples of those last time. I don't know, it's not good. And the reason for that, maybe I can speak to this next piece. Okay, so we got 10 minutes left, so let's do this next piece. Okay, so can we add these things together? Can we do these things together? The answer is yes. So, so for the VAE, there was like 2 parts. There was the reconstruction part that was basically just like the autoencoding part, right? I have my original data, I want to reconstruct it. That's an autoencoder. And then what I did was as I used the KL divergence to impose a distribution on my latent space. Now, when you learn about GANs, hopefully this came through. GANs do something very similar. GANs also want to impose a distribution on your latent space, and then generate data from that latent space. But they do this in a very different way. So for VAEs, you're actually learning the distributions. You're actually learning like in the end, you actually have like these networks actually represent the underlying distributions. In a GAN, you don't have a distribution that represents the encoding of the object or the data. There's not a function here that takes you from the image and puts you into the latent space. You just start with the latent space and you learn to generate data that comes from the data distribution. And you do that by playing this game where you actually have real samples of your data, and then you have samples of the data that your network is learning to generate, and you have two networks. One is the generator network, so you do have a generator. This is the thing that's sampling your data, that's parameterized by some latent space. But then you have this discriminator that's trying to tell the difference between what's real data and what's generated or fake data. And you keep playing this game where you train the discriminator to be as good as possible at this given the state of the generator. And then once you have a really great discriminator, then you kind of swap this game around and you train the generator to using the signal from the discriminator to be very good at generating data that confuses the discriminator. And then once you get good at that, then you switch back around, and the discriminator now is trained to get very good at discriminating between the two, fake and real data, or generating and real data. And then we just kind of keep going back and forth, back and forth. And if we do this right, what we get in the end is we get a network that will generate for us data that looks that is sampled very well from our original data distribution. So it doesn't necessarily live in the thing that we generate is not necessarily a data point in our data set, but it's very close. And so what we're able to do in this case is learn very complicated distributions because we don't have this additional piece of having to learn to encode. We just simply have some way of basically the most basic way of thinking about it is we have some sort of distribution of our latent space, and we're learning to transform that into the distribution of our data. And we do this through playing this discriminator generator game. So again, there is some parameterization of a latent space for GANs. It's just we don't have the encoding piece that takes us from the image into the latent space. But we can combine the idea of an autoencoder, which does have that, with the idea of a GAN. And the way this works is we actually choose again like a Gaussian some sort of distribution for our latent space, and instead of using KL divergence to match that distribution with the distribution that we actually have from our encoder, instead of using the KL divergence to do that, what we do is we use the GAN to match those together. So the encodings that we get, so the distribution that we get from our encoder, that generates for us that generates for us fake data. And then we take samples from the distribution that we want it to be like, and then we play this GAN game where we train generators and train discriminators so that the distribution here becomes indistinguishable from the distribution that we really want. So it's very similar in style. Our autoencoder is trained exactly the same way. We're gonna maximize this reconstruction piece, but we use a GAN instead to do the matching of distributions rather than the KL divergence term that we got from the VAE. Does that make sense? What the difference here is? So it's very, very, very similar. Both of them have ways of imposing a distribution on this space, our latent space, but it's just done in different ways. One is using KL divergence, the other is using the GAN procedure, the adversarial procedure. Any question?
Wait, so when you say GAN, do you mean the full kind of the full network of generating image and having the generator and the discriminator?
Yep.
Or is it just a discriminator?
Nope. This has both again.
Okay.
So there is a network here that's generating, samples, generating fake samples from this. That's learning to generate fake samples from this, and the point is that this is all, there are basically like two heads of this network now, right? So there was also two heads of the other one. There's a KL head and the reconstruction head. This one now, the head for this piece comes from the GAN, from like both pieces of the GAN. So it's going to take, again, this is the fake data that we're generating that we want to look like this distribution, and so we have a discriminator that's trying to tell the difference between these, and then a generator, which is this piece that is trying to produce really good fakes that fake out the discriminator.
So the generator then is kind of like
exactly. This is the generator. This right here is just the discriminator piece.
Okay,
That's
what I was.
Yeah, sorry, I didn't say that very clearly at first, but now I see what you're asking. Hopefully that helped.
Okay.
Exactly. So yeah, the generator for the GAN is the encoder from the autoencoder piece. Yeah. Cool. Yeah. So again, these are both procedures for matching distributions, and we can choose one or the other. And the people who came up with this, actually the same. So adversarial autoencoders. So Ian Goodfellow is also an author on this. Was the famous author on the GAN papers, but with a couple other people. And they have these really interesting results. So again, using MNIST, we have a couple of different things we're doing here. So here we're imposing, we want our latent space to be two-dimensional Gaussian, right? The distribution to be two-dimensional Gaussian. So what we have here is two columns. So look at the first row. So in the first column we have the results from using an adversarial autoencoder, and then the second column we have the results from using a variational autoencoder. So there's a couple things that should stand out to you. One is that this actually looks like what you'd expect from a Gaussian, right? So like if you just got rid of the colors, this looks like this is from a standard normal. So this looks like an isotropic distribution centered at 0, 0. While this does not. I mean, it kind of is. It's kind of got some sort of circular behavior to it, but it's also got some really like skewed areas of this. So like already, this is already matching the distribution better, the distribution that we wanted better than the VAE does, and that's just because the GAN has the GAN has got more. It has an easier time of matching distributions, just the way that the GAN procedure is done. The second thing to notice here, this is test data, right? So this was trained on 60,000 images, and now we're looking at 10,000 test examples. This fills in the space within the Gaussian, right? Like there's no gaps, where there's like tons of gaps here. And the way to think about that is that like we're filling out this entire data manifold in 2 dimensions using the GAN process for matching distributions, and this is not. This somehow has gaps in it. And so maybe the way you can see that is that you just get like far crisper reconstructions here, or like generated data, when using the adversarial autoencoder than you got with the variational autoencoder. So like instead of these things that kind of look like numbers that, if you think about it, like they don't quite live on the data manifold, or like things that are actually handwritten digits, but like that are really close to it. These are more like these look more like actual handwritten objects. So that's pretty cool. Like if you just think about, like if you stare at this for a little while and look at the color mapping from down there, you can see how this is actually just taken directly from this, right? So like these blues here are the zeros. So like see the zeros are up there in this kind of upper left-hand corner. The same thing over there. And as you go across, like stay at the top row and go across to the right, you're going to run into some 5s, and then really quickly run into some 3s, and then back into some 5s, and then some 8s, and then some 2s, right? And so, you know, this is like a direct correspondence between these two pictures right here. One's is showing you the representation in 2D latent space, and the other one is showing you the generated image from that part of space. What's also really cool here is that, you know, you could easily do this for the VAEs. Well, you can do this when it's a mixture of Gaussians, but like if you get more and more complicated distributions, it's going to be harder and harder to do for the VAEs, because the VAEs, to be able to optimize that KL divergence, you actually need like you need to be able to compute that directly, like analytically. You need to be able to write down how the parameters appear in that KL divergence term. You don't have to do that for the GAN, because the GANs are simply going to sample from it. So you can get far more complicated distributions on your latent space. So like here's some kind of crazy one that is like 10 different Gaussians, no longer you know, nice and spherical, but these are these ellipsoids. So you have far more variance one direction than the other, and then they're sort of all arranged around 0. And this is learned using the adversarial encoders learned to again fill in the whole of this latent space very well, again without gaps and filling out like all of the different Gaussians, where the VAEs had a really hard time doing it. And what you can see is the VAE really concentrates probability around like the modes of the distributions rather than kind of filling out the distributions, like especially like in getting the proper variance in all the terms. There's 10 here because there's 10 digits, so you would kind of hope that you would have seen that like, hey, each one of these little tongues corresponded to 1 digit, but there wasn't enough information in the training procedure to be able to do that. However, there's a couple of different takes on adversarial autocoders that make them really fun, and again, kind of express the like Lego aspects of neural networks, and that is that if you just slightly adapt the training procedure and include labels into the discriminator, then it turns out that you actually do get that each of these tongues in this mixture of 10 2D Gaussians is mostly dominated by single classes, and in each of these tongues you get this individual parameterization of the so in each of these tongues, like what's 0, so blues, like this one right here, you get this, and what you can see is that like each of these like stylistically is very similar. So like as I vary, so if I like reparameterize these so like they're all kind of like laying on top of each other, and I do this generation, then what you see is that like you know, like where the strokes are darker, they're darker in both spots. Where they're slanted to the right, they're slanted to the right in both spots. So yeah, that's pretty cool. And then this is just showing how like you can learn really complicated distributions. Like if you want to impose this Swiss roll distribution on your data, then you can do that as well. And this is really cool because this is giving you some parameterization that is like going from 0 to 9 in this like along, like as you unroll along here. So that's really cool. There's lots more here, but I can go some over time.
So with the figure 8, right there in the center where 0, 0 intersect.
Which picture?
The top one.
Uh-huh.
So I'm just trying to get an idea of like the application of this. I'm guessing the application of this is to kind of boost up a weak data set. But in this example, right there in the center, it seems like that's going to be a place where you're going to be mislabeling data.
Well, that's a place, this is really interesting, right? So that's a place where the examples that look like other examples go, right? Lots of 3s look like 8s. Lots of 1s look like 7s. You know, lots of 9s look like maybe some kind of 5s or something like that. Those kind of go in there because they do look like the other class. And that's what's really cool about like learning these kinds of representations of these latent features is that the latent features are really showing you like, even though there are different classes, which members of these classes are like actually look like members of the other class. Yeah. You know, this is definitely like a toy example, right? MS is always a toy example. It's really simple. It's got 10 classes, but you can see the power of this. And I won't go through this deeply because I know time's up, but you can expand this even more by providing labels to the to the decoder part of this, and separate out your encoding into like a label encoding and a style encoding. So you can think of this as like each one of these rows has like a different set of values for the style part of this encoding. And then you just vary the label part of the encoding. And so you can see like every row here is all of the same style, you know, whether that's like kind of ghosting writing or like very thick writing or like tilted writing or whatever, very loopy writing. And you have something similar for the Street View house number data set, where again, as you change the style vector, that's giving you a different style of how the numbers look, but you get 0s and 1s and 2s and 3s and 4s all the way through. So just kind of cool ways that these things can be used to kind of break apart the different explanatory factors of your data. Okay, yeah.
Well, at least from the administered data set and the virtual encoded from Sparvator and the Unilo VAE, I'm just curious about whether it has become a popular or a new trend in the GAN community.
No, it weirdly like adversarial autoencoders aren't still as popular as VAEs, mainly because they're harder to train. Whenever you have a GAN piece, they're just harder to train. This mini max game you play between the two, this discriminant generator is always tricky. So it's much more straightforward to train a VAE, even if you get worse results. Good question. All right. Thanks for letting me go a little bit longer.
So Monte.
Next week, recurrent neural networks.
So, a generator, I remember in GAN, we have generator trees. So tree here it seems like tree is identical like tree.
Yeah, the same is definitely a real non-linear adaptation from the latent space to data space.
So here, I remember.